So in this section of the presentations, we're going to talk a little bit more about the digital signal processing that leads to the software-defined radio at the physical layer, all supported by the RFSoC. So we'll consider first just the history of QAM architectures, looking back to how baseband, IF, and now RF sampling has come about. We'll then discuss sampling and first-order zones and second-order Nyquist zones, and then look at the ADCs and the DACs, and how we do some very interesting new bits of signal processing to make sure that we can work in both the first and the second order Nyquist zones. So in this section we will review quadrature systems and look at the front end QAM, Quadrature Modulate, Quadrature Demodulate, which is a core part of the RFSoC for software-defined radio implementations. We'll remind ourselves of the evolution from baseband sampling some 20 years ago to hundreds of megahertz samplers and so-called IF sampling, and what we have now with the RFSoC RF sampling. A reminder on the sampling theorem, and then just some work to talk about the second order band and how that affects the sampling theorem. Aliasing will be a feature. We'll be looking at second order Nyquist therefore for RF ADCs. We'll implement mixed mode and tell you why that's important for RF-DACs, and then we'll talk about the reconstruction filters we require at the output stages of the RFSoC for our first and second order Nyquist bands. So let's remind ourselves of the QAM Transmit and Receive architecture. And in this simple diagram we can see on the left hand side we want to transmit information. It's a QAM modulator. On the right hand side we want to receive information, and it's a QAM demodulator. And the physical layer of many radio architectures, whether Wi-Fi or GSM or 5G and 4G, are based on quadrature amplitude modulation or QAM. And it might be QPSK, it might be 64 QAM or 1024 QAM, but it's all basically this front end physical layer. With the RFSoC, what we now though have is RF-DACs and RF ADCs. So we are now sampling at gigahertz, and we've now some very interesting approaches to signal processing. Sampling a very wide bandwidth and choosing to channelize, use digital up converters, down converters, in order to ensure we can receive the right channel. So the digital up converters and digital down converters, well, we'll see these later when Louise will present on using the DACs and DDCs in earnest. So quadrature modulation, if that's something you've not familiar with or forgotten about, basically we have an I and a Q channel, and we can transmit two channels in the same carrier because we're going to use cosine and sine oscillators that will be orthogonal, and therefore it's actually just more efficient use of bandwidth. So we occupy the same bandwidth, but we have two signals on that particular channel. So a QAM system, without really considering the digital side of things, on the left hand side we have an information signal, signal 1 and signal 2. We then modulate with an oscillator, so maybe analog as in this case. We add the two signals together, and the two signals are transmitted over the RF antenna. Now, further down the left-hand side, where it's 4G, 5G, whatever it might be, not really a concern of this presentation. So looking at this from a spectral point of view, we can see that we have one baseband signal in the I channel, and we have another in the Q channel. And when we modulate the I channel and we modulate the Q channel, we then combine these both, and we have the composite signal that's sent, and it's bandwidth efficient because the total bandwidth here is 2 FB, and both of the basebands have been FB hertz. So that's a very simple motivation for QAM. It's spectral efficiency. The demodulation side, well, if we've transmitted something as QAM, hopefully we can retrieve the signal back. So the signal will be received on a suitable antenna. So it'll come in. We will then put it through appropriate gain stages. we'll have oscillators to bring back down to baseband, some filtering stages, and then hopefully everything's ready on the right hand side now to receive in my radio system. Again, 4G, 5G, Wi-Fi, whatever that may actually be. So we can see here that if we receive the signal that we just transmitted a few seconds ago, then after we mix down to baseband in the cosine and in the sine channels, we get a couple of baseband signals. Of course, we get components at twice the carrier, and we filter these off and we get back to the baseband. Now, there's many aspects of synchronization, phase synchronization, frequency synchronization that we must do, and we will do in the RFSoC, but that's not something we have the time to present today. But clearly, synchronization is a core part of radio architectures. Now, remind ourselves of modulation. So just to see how we ended up with RF sampling, if we remind ourselves about where we've been in the last few years, well, we've been doing AM modulation for many, many years, taking a baseband information signal, modulating with a carrier. So the baseband information is then modulated onto a suitable frequency. And then, of course, we receive that frequency. And when we receive the frequency, we put through a band select filter. We then mix down to baseband and we get back to the original information signal. So at the receive side, we have the AM modulated signals received, and we bring that back down to baseband, and we'll remove this signal over here at twice the carrier. So that's my basic demodulation, 101, maybe from the 1950s. We, of course, have the concept of the super heterodyne transmitter receiver, which has been around for some time. And one of the ideas here is it will take our baseband signal and then we'll modulate from baseband to an intermediate frequency. And this is for ease of design. And then after the intermediate frequency, we'll then modulate again, and we'll modulate that onto our suitable RF signal. So we'll end up with a signal at this particular frequency band here. And there's a little bit of filtering to do to filter out images, but that's the super het, which has got two stages of modulation. And in fact, that is going to be something that we will call intermediate frequency, or IF systems. As in other presentations, some of these slides have notes below. I won't always refer to the notes, but if you're watching the videos and you want to see what's in the notes for a bit more detail, just freeze frame. So what's happened really in the last 20 years is those digital to analog and analog to digitals have got faster and faster. And that was a presentation I did in my previous section, where I just pointed out the speed of ADCs and DACs from a few hundreds of kilohertz to now gigahertz. And if we consider what's happened over the last maybe 20, 30 years, then get all the way back maybe to GSM radio or what we might call 2G, before 3G, 4G and 5G, then everything was down at the baseband, and that's where the digitization was done. So down at the baseband, my speech and perhaps data goes onto my DAC, which is running at the order of kilohertz. And we then have an analog oscillator, maybe my IF oscillator, and I'll take that signal to an intermediate frequency, and then I'll have my RF oscillator, bandpass filter, and I'll send my radio signal. So that's the kind of 1990s QAM architecture for mobile radio. And if we look at the receive side, let's receive that signal. And we have a bandpass filter, an RF amplifier. We choose to use an IF system, and this IF system will bring the signal down to an intermediate frequency. Then another oscillator brings it down to baseband. Now note that the digital part is just this little part down here. And the analog in the red is actually most of the front end part of the QAM. And the same was true of the transmit side. If we look again, most of the block diagram here is analog, and the digital is just the baseband for my speech and data audio. So things speed up. We now find that DACs and ADCs are now faster by the time we get to the 2000s. So now we're perhaps at hundreds of megahertz. So this time we can do our digital baseband processing, but then the IF oscillator that we had before is now digital. So it's now lookup tables, sine and cosine. And then we'll put through a DAC, which is the order of hundreds of megahertz, to our intermediate frequency, and then a final RF stage to take me to my RF transmit frequency. And at the receive side in the 2000s, we of course have the received RF antenna, bandpass filter, we demodulate, mix down to the IF stage, and then we have a final IF demodulator, which is digital. And we can now see the digital part of the circuit or the system is now much larger than it was before as the speed of DACs and ADCs has improved. So where are we now? Well, 2015 plus from Xilinx and the RFSoC, we are now sampling at gigahertz. So actually we don't need the IF stage. We can go straight from baseband all the way to some gigahertz band. So now if we look at the digital section, we have our RF complex oscillators, our digital baseband, whatever that might be, and then my DAC is running at gigahertz. And I still, of course, need the RF appropriate filters, and I need RF gain stages, so that doesn't change, doesn't go away. But that's now where we are in the 2010s, 15s, and of course today as we're presenting with the RFSoC. And at the receive side, well, we also are using RF ADCs. So we are sampling at gigahertz, and my oscillators and so on, well, they're running at gigahertz, and these are all software-defined radio, right up at the QAM physical layer stage. And then the rest of the digital baseband processing, my 2G, 3G, 4G, 5G, whatever it might be, of course, will be done on the RFSoC FPGA. So sampling, I'm sure everyone knows the sampling theorem, but let's just see how that's kind of changing a little bit for some of the things that we now want to do. So remind ourselves of what do we want to retain? Well, here's a simple sine wave, and I would like to retain all information so that I can reconstruct the sine wave. So I'll need to know the frequency of the period, I'll need to work out the amplitude, I need to make sure I get hold of the phase. So if I sample the signal, what rate do I have to sample in order to retain all information? And there'll be no quantization considerations here. That's not something that's in the scope of this short presentation. But of course, the RF ADCs and DACs quantize, and there will be quantization noise, and that's something we take into account in terms of the integrity of the signal. But we'll just look at sampling here. So I think we all kind of know the answer, but let's have a quick visual. So if I sampled at 800 megahertz, then that would give me round about 8 samples per period for this 100 megahertz sine wave that I'm sampling. And if I just take a look at the samples and I consider, could I get the frequency and the phase and the amplitude back? Yes, of course I could. So that seems like a pretty reasonable sample rate. What about we sample at 3000 megahertz or 3 gigahertz, which for this particular 100 megahertz sine wave would be 30 samples in one period. Oh, well, that seems pretty good as well. Maybe higher than necessary, but it seems to work fine, so we'll give that a tick as well. Maybe let's go the other way. Let's reduce the sampling rate. It's always good to be running at the lowest possible sample rate in a DSP system. And if we considered sampling the 100 megahertz sine wave at a sample rate of 100 megahertz, then that kind of looks too slow, and we would see that we appear to get a DC signal, so probably not working. And if we sampled my 100 megahertz sine wave at 80 megahertz, so the sample rate is lower than the actual signal, then it doesn't seem to work at all. And we have the original sine wave at 100 megahertz, yet when we take samples, we're missing a lot of time variation, so it appears not to be working. And of course, I'm quite sure everyone knows in this course, this is in fact aliasing. So, and aliasing, we don't like aliasing. We have to avoid aliasing and anti-alias filters and sample at the right rate. but things have changed a little bit with some of the things we're doing with RFSoC. So that's what we're coming to. So just some signal frequency terminology. The Nyquist rate, we're going to call Fn, and that's going to be twice the maximum frequency component present in a signal. And very often our signals will be baseband. So if we talk about a baseband signal, then that usually means it starts round about 0 and goes to some value FB. And if we talk about a band limited signal, well, that means we can identify a lower and a higher frequency, and most of the energy of the signal is within those two frequencies. And the Nyquist rate is going to be twice the maximum frequency component present in the signal for f of n. So my Nyquist sampling rate, if I take a signal that I'd like to sample, so we saw this kind of earlier on, if I want to retain all information, I've got to sample like greater than twice FB. So that's the standard Nyquist sampling rate. Identify actually the bandwidth of the signal, sample it greater than twice the bandwidth, and you retain all information in that signal. And of course, if it's a baseband signal, then FB is actually the same as Fmax, the maximum frequency. So why sometimes people say sample at twice the maximum frequency. So we discussed that earlier on. So aliasing then. Aliasing appears to be an issue, but let's try and turn it into a feature. So here's the example from before. We've sampled the 100 megahertz sine wave at 80 megahertz. And if I reconstruct what I've created in my digital system, then the blue signal I can see, it is a sine wave, but it's at the wrong frequency. In fact, it's at 20 megahertz. So the 100 megahertz, when sampled at 80, has aliased down to 20. And of course, that's apparently wrong. It's also nonlinear as well. And it's something that we want to usually avoid. So just to remind us again of what will happen when we are sampling our signals. So if I had a 100, 250, and 400 megahertz sine waves, and I sampled at 1 gigahertz, then, okay, my Fs over 2 is equal to 500 megahertz. So by the Nyquist sampling theorem, everything below 500 megahertz, yes, I should be able to retain that information. And what will come out the other side if I reconstruct will be 3 sine waves at 100, 250, and 400. Now here's another experimentation. What if I were to sample 3 sine waves, but this time it's a 900, 750, and 600. And I'll sample at 1 gigahertz. Well, this time, well, the Nyquist sampling theorem, greater than twice the maximum frequency, I'll call it out as here, then I've violated that because 900, 750, and 600 are all greater than 500. So we'll sample, and then when we reconstruct, we will find aliasing happens, and actually the 900 aliases to 100, the 750 to 250, and the 600 down to 400. And so on as we go to higher frequencies, as I get to 1100, 1250, and 1400, sample at 1 gigahertz. Well, we're not sampling at greater than twice the maximum there, so once again they will alias down to 100, 250, and 400. And if you want to know why those are the values alias to, you can do a sketch, run a MATLAB simulation, quick bit of math, or just look at the slide above. You can see how the process of aliasing is actually happening. So you can see the alias here, and we can easily work out what the input frequency will be for a given sampling frequency to create an output frequency. So sketching this in a frequency domain, what we just saw was that if I had a 100, 250, and 400 hertz, and I sample and reconstruct, everything's good. No aliasing happens. But if you were to input signals that are at 900, 750, and 600, well, yep, we saw that will alias down to the baseband, and aliasing has happened here because they're above Fs over 2. And similarly for the 1100, the 1250 and 1400, yep, that will alias down to baseband as well. So if you're looking at a baseband signal, then how do you know whether that baseband signal was generated by the 100, 250 and 400, or the 900, 750 and 600, and the 1100, 1250 and 1400? And the answer is you don't. So we have to do something to make sure that we only allow one band through. So we need an anti-alias filter. So aliasing seems to be a bit of a problem, but actually maybe we could now use this as a feature as we start to do RF sampling. So here's some numbers similar to what David will show you shortly. We're going to be sampling in these pictures at 4 gigahertz. David will be sampling at 4 gigahertz in the examples coming up, but actually 4.096 gigahertz, but we'll keep the numbers simple here. And I'm going to input this red signal here, which is a 3.6 gigahertz sine wave. And sampling at 4 gigahertz, then I can see that I missed quite a lot of transition information or energy of the, or amplitude of the sine wave. So sampling at 4 gigahertz, I can see that I missed some of the amplitude variation of the 3.6 gigahertz sine wave. And the blue samples that I end up with, if I were to reconstruct, I do get a sine wave, but it's a sine wave at 400 megahertz because we've aliased. So still a sine wave, 400 megahertz. I can see there's a phase change as well, but I'm not going to worry about phase change. I can correct phase changes. I can correct spectrum flippings as well. So these are not concerns to me for fixing in the baseband. And if we look at this simple diagram, there's the alias feature happening. So the 3.6 gigahertz has alias down to 400 when we sample at 4 gigahertz. So that's a problem. But of course, as we briefly mentioned in the previous presentation, and again in this one, it's actually going to be a feature for us. So the RF spectrum we looked at before, and if I would like to be retaining all information here, what I showed you in the last presentation was, yep, that's all very possible, and all we have to do is make sure that we sample with an anti-alias filter across 0 to 2 gigahertz. So get all the information from 0 to 2. We filter everything that's above. So we'll pick out this band here, and anything above, nope, that's gone. We don't want it. And if we do that, then we will find that everything's good. And there's a single input, single output system. So we can take it to our FPGA and do our DSP or our software-defined radio, however we wish to refer to that. And if you wanted this higher band, so actually if we want these frequencies here, which are above 2 gigahertz, well, now we exploit aliasing. And that's exactly what we can do by taking our sample rate at 4 gigahertz. We put the 3.6 gigahertz sine wave in here again, just for observation. We can see that goes down to 400 megs, so that's great. So as long as you have the analog bandpass filter, again, as we discussed earlier on, remove all of the energy above 4, remove all of the energy below 2, great. We will be able to take this band 2 to 4 gigahertz, and we can bring down to 0 to 2 gigahertz, and we can get the information at 2 to 4 gigahertz in the RFSoC. Now you might be thinking, oh, the spectrum has flipped and the relative position of signals has moved, but that's not a difficult issue to deal with. We can easily flip that spectrum round with just some very simple processing. And of course, it's up to you to remember or to note where your signals have gone. So if you are interested in a particular band here, great. After aliasing, where's that going to be? Well, that's your responsibility to say, oh yeah, it's going to be here. Or if you were interested in some other band that's perhaps down here, great. After you alias, where's that going to be? Well, it's going to be here. So again, you just have to track where that's going to be. And that's part of the frequency planning, part of the kind of new paradigms of working with RF sampling in the RFSoC. So Nyquist zones, we can go to higher Nyquist zones. We will limit ourselves at the moment to Nyquist zone 1 and Nyquist zone 2. That's what David will show you. But in theory, we can go higher. And that's something that will undoubtedly happen over the coming years as the analog front ends get faster and faster. So the whole business of deciding what type of anti-alias filter or bandpass filter, that still has to be done by the engineer. And although we can do lots of excellent bits of signal processing inside the RFSoC, you still need the front-end anti-alias and reconstruction filters. So we got to get that part correct. So we have to understand about spectral imaging and alias bands. And we have to be aware as well that we must meet the Nyquist sampling criterion. Whether you're just working in the first order band or the first order Nyquist zone, or you're working in the second order Nyquist zone, you have to make sure you get it right. So the fundamentals are still there. We're just extending a little bit to start to think in the second order Nyquist zone, where our anti-alias filter is now a bandpass filter of some shape or form. And in these presentations, I'm talking about sampling at 4 GHz. Of course, in many systems, you will maybe choose not to go all the way to 4 GHz, and you may use some other frequency. There's other things to learn as well about frequency planning. So there are some gotchas with harmonics that will appear from RF and gain stages. So Louise later will take us through some frequency planning and some of the additional things you have to think about to ensure that when you find your signal of interest in the baseband, you minimize any issues with harmonic distortion and some from the nonlinearities in RF and gain stages. So again, a number of new things to understand and consider if you're using RFSoC for the first time. So let's consider the digital to analog conversion side of things now. So we'll keep this nice and simple and kind of standard digital to analog conversion shown in the screen. So we're going to take just samples at a given sample frequency. And we're going to then put them through a zero order hold, which is a simple standard way of going to the analog world. And therefore, for each sample that goes in, we kind of hold the voltage constant for one sample period. And the output that comes out, if you have a look at the final output, we can recognize that it's probably, contains the information of the digital input signals. But we have these steps now. And we recognize that these steps are not part of the original signal. Now, if we consider what's happening in a frequency domain sense, the zero order hold, if I look at the frequency response of the zero order hold circuit, I can see that it will give me energy in the baseband, or the band of interest, 0 to fs over 2, but also we get energy in the higher order bands, and that energy, when you add it all together, that's what's creating those kind of high frequency steps. So I realize what I need to do. What I need to do is I need to decide that somehow I'm going to filter out those higher frequencies. So I just need to get rid of these values up here, and that's good. I do also notice there's a bit of a droop here. So perhaps I need to try and compensate that with some sort of compensation filter. So we often do that, a sin x over x correction. So we'll review what that means for the RFSoC in a few moments. So we take the steppy output, the zero order hold output, so it's now an analog signal. So this is an analog signal, but we want rid of the steps, which are these higher frequencies. And we do that with the low pass filter. So ideally we cut off at fs over 2. So we remove all of the energy up here, and we're just left with 0 to fs over 2, and we get a nice smooth signal, and that smooth signal, of course, has taken out the steps, and that's my baseband 0 to fs over 2. And assuming my original signal was sampled correctly, I'm very happy because I started with only information from 0 to fs over 2, and after all my processing and my reconstruction, I've still only got energy between 0 and fs over 2. So just a little more detail. Here's my zero order hold pulse. That's what I'm essentially using for each of my digital samples that comes in. I'm holding constant for one sample period. And as we sketched in the previous slides, when I look at the spectral characteristic of this, this is the response I get, the sin x over x, or the Sinc type response. And my energy is definitely there in the 0 to fs over 2 band. It is attenuated a little bit, and 2 over pi is in fact about 0.6. And if you want that in dBs, that's about 3.92 dBs. So there is some attenuation here, but that's okay. We can fix that in a moment, or it might be of a level that it doesn't actually cause a concern. So if we look with just a higher order Nyquist bands, or higher order zones, then we sample again at, let's choose 4 gigahertz again. And then here's my signal coming out of the RFSoC, RF-DAC, digital to analog converter. This is now an analog signal. So we've left the digital world. And if I look at the spectrum of this signal, I can see the sin x over x form. So there's my band of interest, perhaps. And then these are the higher order bands that are caused by the steps, or the high frequencies created by the zero order hold process. And to remove these, well, I know what I was doing. To remove these, I will use some form of low pass filter. So again, I've sketched that on the screen here. So we come from the RFSoC DAC. This is the spectrum of this time domain signal here. So this is what it looks like in the frequency domain. And then we've got our low pass filter, a reconstruction filter. And I only want to keep a hold of the first zone here. And if I then look at the analog output, well, most of the energy is from 0 to fs over 2. And these higher order zones, or Nyquist bands, I've done a pretty good job at attenuating. So off my signal goes at some frequency, in this case round about a gigahertz if I'm sampling at 4 gigahertz. So if I look at the droop here, then this is actually dropping down by about 3.92, about 4 dBs. So if I could put a filter with a bit of a lift here, then that would be a good idea to try and flatten off my Nyquist zone 1. And where do you put that filter? Well, you could try to maybe modify this filter here in the analog world, but really that's going to be too difficult. So of course, like many things, we'll do this digitally. So down here somewhere in the RFSoC, that's where you can put your filter with the lift. And if we zoom in a little bit, we can see that, you know, my signal of interest is around about 1.7, then it's down 3 dBs. So that's well, we'd rather it wasn't down 3 dBs. So once again, we will put in a lift. So there's a sketch, and the green, the inverse sync is shown. And if I can create that filter digitally, then I can flatten off the Nyquist zone 1. And zooming in, you can see this green example. And this is one of the filters taken from the RFSoC device. So using that filter, we'll place that somewhere in the RFSoC, and it's on the FPGA, and we do the correction before we go to the RF-DAC. And then once we send the signal out, we've done the correction, and so again we go through the low pass filter and we create our analog output signal. Now, here's some of the exciting things we're now doing with the RF-DAC side of things. So if I want to start using the second order Nyquist zone, now I've already demonstrated that's possible and quite easy to understand for the RF-ADC, for the analog to digital. We're at the other side now, we're doing digital to analog. So how can I create energy in the second order Nyquist zone? So what we're going to do is, rather than using the zero order hold, we're now going to do an analog process to use this pulse we'll call the RF mix mode pulse. So within one sample period, we're going to, for the first half, have a positive amplitude, and for the second half, have an equivalent negative amplitude. And it's important to realize this is actually done in the analog circuitry. This is not a digital process. So it's not part of the FPGA and the logic fabric. So if we just compare the time domain of the zero order hold and of the mix mode, so the time domain was done with the standard zero order hold where each sample is held constant for one period. And we get the steps, and well, we saw how to address that. For the mix mode, again, that's an analog process. So it's done after the digital to analog conversion has been done. And we've switched the signal to an equivalent negative amplitude during each sample period. Then, well, we get the signal, which looks a little bit like an AM modulated envelope, and it is to some extent. And of course, you can see the original, analog signal in here for the zero order hold, and something equivalent. You can obviously see the same envelope shape for the mix mode. If I look at the spectrum of the mix mode, then I see that I still have energy in the first zone, the second zone, the third zone, and so on. But now the distribution of energy is different, and most of the energy is in zone 2, or the highest level of energy is in zone 2. And in the kind of Nyquist zone 1 and 3 and so on, well, we have a attenuation, as we had maybe for the sinx over x. But I've now pushed energy from Nyquist zone 1 into Nyquist zone 2. So this is good. So this is improved if I want to target my output into the 2 to 4 gigahertz band. And just reminding ourselves, what would it be with zero order hold? Well, zero order hold has a classic sinx over x sync, and there's my energy in zone 1, and we see the sinx over x shape. Well, we've now improved things if we're targeting zone 2, as we've shown here. And what we can do is now work out a way of extracting zone 2 with an analog form of reconstruction filter. Looking at this in a dB scale, we can see that there's definitely some attenuation here. In fact, we're actually 3 dBs down in Nyquist zone 2 when we use the mix mode. But it is pretty flat. So perhaps we need a filter that's got a gain of 3 dBs and will compensate for the droop. And of course, we can do that, and there's going to be direct support for that. And there is direct support for that in the RFSoC Gen 3 devices. So here's the contrasting of what we would do with the zero order hold or the RF pulse mix mode reconstruction. So we can see at the top, this is where we started, zero order hold, just targeting energy in 0 to 2 gigahertz band. So this is the band zone 1 that we want. And the reconstruction filter, the low pass filter, the RF filter, will remove the energy above 2 gigahertz. And of course, I'm using very idealized filters here. Life can be a little bit more difficult in the RF world, but I'm just sketching what we would desire. If we choose the mix mode, then okay, the signal is converted to analog, and then we put through the mix mode pulse. And if I look at the spectrum, we have the highest level of energy in zone 2, which is good. So if I put this through my bandpass filter, then I'll be retaining the energy in the bands 2 to 4. And I can see that's happened, and I've reduced most of the energy in the other bands. So in this case, I've been able to retain the energy in the 2 to 4 gigahertz band, which for my particular application I desire. Now we've got to make the choice between which zone you're going to target. You cannot target both at once. So whatever type of system you choose to build with your RFSoC, these will be some of the early engineering design decisions you've made. Are we going to use Nyquist zone 1 or are we going to use Nyquist zone 2? And once you've made that decision for the analog to digital, for the digital to analog, you can then start receiving your signals and generating your signals in one or other bands. And one of the things David will show you is working in both bands, 0 to 2 and 2 to 4 gigahertz, depending on which particular mode we choose. So what we looked at were quadrature systems. We looked at the first and second order Nyquist zones in the RFSoC at the input and output stages, and that brought to our attention aliasing as a feature and RF mixed mode. Topics coming soon, well, Louise will talk about DACs and ADCs in more detail, and also frequency planning, information about the harmonics and how we begin to plan our frequency domain and sample rates. David will be showing some real-time spectral analysis and also showing the design of real systems, top to bottom, start to finish, using the PINC environment. Other things that unfortunately we don't have time for today, but please get in touch if you want to know more. Building and designing NCOs, and the very important frequency and phase locking and synchronization. Design of OFDM systems, which are particularly prevalent in 4G and 5G. And of course, knowing how to design efficient digital filters, polyphase filters, parallel filters, and using the many features of the FPGA. Thank you.